Hello Math 1316 students, let's begin Lesson 5, Trigonometric Functions 1. Previously, from Lesson 1 to Lesson 4, we had been studying trigonometry as a part of geometry. In other words, everything static, more or less. Indeed, we went through a lot of application problems based upon static pictures, remember? Now, from this point on, from Lesson 5, we have to take a drastic change of viewpoint. We have to reestablish everything based upon variables and their relations. What's the starting point of the variable? Our independent variable, the radian angle. That's the starting point. I hope everybody remembers the definition. Theta is S over R, the arc length over the radius. With this rule, we start from a point on the positive side, right-hand side of the x-axis, r, 0, and travel counterclockwise along a circle of radius r centered at the origin. What if I travel clockwise? We're going to get the negative of that angle. Negative angle. So if this is, say, some alpha, this will be some negative. As a matter of fact, this will turn out to be alpha minus 2 pi. Anyway, this is positive, that's negative. I said alpha versus alpha minus 2 pi. Is 2 pi that important? Well, yeah, everybody will remember that, I hope. That's coming from the full rotation. If you take a full rotation, then you're going to get a full circumference instead of just an arc length, right? So the numerator arc length becomes the circumference, 2 pi r, and divide by radius r, you're going to get 2 pi. So what do you mean by adding 2 pi? From here, wrapping around once more and coming back to the same place. What do you mean by adding 4 pi, wrapping around twice, again coming back to the same place? Now what do you mean by subtracting 2 pi? From here, wrap around backward, coming back to the place. Basically, it's this one here. So alpha minus 2 pi. And then, of course, alpha minus 4 pi, wrap around twice, minus 6 pi, and so on and so forth. So we can wrap around the circle arbitrarily many times, forward or backward. Therefore, we come up with this conclusion. Theta plus 2k pi come to the same place theta. Here, I'm not using the equality notation because, after all, left-hand side and right-hand side are not equal in terms of real number arithmetic. Instead, I'm using the congruence notation, which is also widely accepted. I come up with the same point in the end. Or you say they are coterminal angles. There are many other terms, but in terms of the formulation, this congruence notation is widely accepted. In any case, please remember this structure. Plus 2k pi, where k is an integer. For any arbitrary integer, plus 2k pi will end up with a coterminal angle. We're going to come back to the same point. If you're already comfortable with 2k pi business, then great, keep using it. If you're not, and if you're uncomfortable, well, in that case, study it and make yourself comfortable, because we have to keep using it anyway. This is very, very important. The angle is inherently periodic with period 2 pi, so any plus 2k pi will yield the same place, same coterminal angle or congruent angle. 2k pi or 2 pi, that's great, but why not using degrees? After all, we can convert any degree angle to radian angle and vice versa by appropriate convergent factor. one full rotation is 2 pi, and that's the same as 360 degrees. So 2 pi over 360, or simplified as pi over 180. That's the conversion factor, isn't it? So multiply by that or divide by that. That way you can change degree to radian and vice versa. We can always do that. So degree versus radian, they're equivalent, aren't they? Why radian? Why 2k pi only? Well, there is a reason, as a matter of fact. So far we had been doing geometry only, so we didn't really have to do a lot of algebraic computation to angles. But if you go higher up, if you consider functions, you may have to. And if you go to the next class, if you take calculus, then certainly that becomes a problem. And you're going to encounter problems that if you use degree angle, you're going to end up getting wrong. There's something called the chain rule in calculus, and that's the biggest problem. Anyway, the chain rule and calculus is for the next course. In 13-16 level, it's not going to create that much of a problem, but still, I'd much prefer to do it right way, and everybody takes a good habit, and that is to use radian angle all the time whenever you have trigonometric functions or inverse trigonometric functions and so on, trigonometric equations and all those algebraic analytic stuffs. When you're doing geometry, it's okay, but the moment you step away from pictures, please use radian angle. Now, why? Good question. Now, I'm about to answer that question, but please be warned. If you think this explanation boring, just stop it and just go to the next video, because I'm about to begin something that is highly theoretical, and it can get a bit deeper, and it'll help you understand the importance of radian expression and the reason why it's better to deviate out of this degree measurement. And yeah, I hope everything makes sense, but please be warned, it may be a bit troublesome, so if you think you're not getting that, then just move on. Otherwise, let's come back to this. Alright, we have angle theta here, and what is the measurement unit of angle theta? Radian measure versus degree measure, or there may be other measures, and we have approved with conversion, right? That's going to be the measurement unit, right? Wrong. That is not the case. Look at the numerator, we have length, and length certainly has measurement unit. You use what, centimeters or inches or whatever, right? Let's suppose we use, say, centimeters here. Now, what's going to be your measurement unit for denominator? It has to be the same centimeters. If you use two different units, you're going to come up with a trouble. You have a centimeter measure here, and then you add some inch there, and later you divide by kilometer there. You're going to have a mess. In different formulation, you may have different measurement units, and maybe you'll have to convert those. But in the same formulation, same quantities must have the same measurement unit. Length must be in all centimeters, or all in millimeters, or all in inches, and so on and so forth. The conclusion, in any case, no matter what you do, same measurement at the top, same unit bottom, they divide each other out, cancel each other out, and they disappear. And what's left is a unitless quantity, a raw real number, S over R. Am I making sense? Angle theta, the radian angle theta, has no unit. It's a unitless quantity. It's a raw real number. So saying that there's a measurement unit of radian or degree, no, that's wrong. There is no measurement unit therefore no conversion factor. You already went through a quantity behaves exactly the same. What kind of conversion? Let's consider this. 61.27%. That's same as 6127. Does everybody agree? 61.27% is 0.6127. Basically, I'm moving the decimal twice, or vice versa. And that is because this percent is same as 1 over 100. So percent is same as 1 over 100. So 61.27 times 1 over 100 is 0.6127. That's what we are looking at in this formulation here. Exactly the same thing is going on here. 36.0 degrees. All right? That's the same as 36 times pi over 100. So this degree expression here is same as multiplying pi over 180. Exactly the same thing as the percentages went on here. All right? So the degree measure here is not exactly a measure. It's kind of like percent. It's just a factor you artificially multiply. All right, now refresh your memory about your experience with percentages. How do you do your percentage computations? In elementary addition or subtraction, yeah, you can just add or subtract percentages and end up with the percentages. But what if you have to multiply? Yes, if you have probability computation, you have to do that a lot. If you just multiply percentages, you're going to get a mess. Because you have repeated multiplication of 1 over 100. Or if you take percentages of percentage, oh, bigger mess. So the best and the only surefire way to calculate percentages is to convert all the percentages to decimals in step 1, and then do all those decimal computations. And then at the very last step, express the final answer back into percentages, just for looks. Or you can even skip that. Me, I usually skip that and keep it as decimal. Very same thing goes on for angles. If you have degree angle, it is best to convert everything to radian angle, and radian measure, quote unquote, is not precisely correct expression actually. Angle is a unitless quantity, so it's not actually a measurement. It's just a real number arithmetic. And then in the end, convert it back to degree. That's how you do your computation correctly. And in 13, 16 level, that's not going to cause humongous deal of trouble because you don't really have a lot of serious computation with degrees here. But in calculus, you will. If you encounter trigonometric functions in calculus, and especially if you have composite functions and chain rule, then no, never use percentages. Never use degrees, just like you should never use percentages. Convert everything to radian, and then get your final answer, and if necessary, convert it back to decimal, or just keep as is. Convert to degree and keep as it. Whatever, you understand what I mean, I hope.